We now have Bruce Damer, all the way from California, to give us a talk on work that he's been doing, and he's been doing a hell of a lot, so I can't go through all of these things. We already know quite a lot what he's doing. I mean, he's a pioneer in various places. He's been working for NASA. He started off Biota stuff and all that kind of thing. And now he's down in London teaching and studying for his PhD in East London.
There's the East Londoners on the east side of the room.
So you might pick up a few tips. Right, so without any further ado then, over to you. Bruce will talk for about an hour and a half, 20 minutes, hour and a half, something like that. Or when you get started, you can stop.
Okay. This talk is about artificial life in general, but also the Evo Grid idea. If you want to know anything more about me or the projects, the Computer Museum, and the Avatar's work and whatnot, it's all at damer.com. If you want to reach me, it's just bruce at damer.com. It's pretty easy. And I welcome any contact. So this little presentation is going to introduce a number of things. What is Biota, which is an organization? What is artificial life, which is a medium or a vision or a dream, if you will? What is the Evo Grid, which is a dream and a philosophy and maybe a cosmology? And then how would, if an Evo Grid ever came into being, how would it affect us as a civilization and affect us inside and our feelings of where we are in the universe? Biota was, I was climbing in the mountains, in the Rocky Mountains in British Columbia, near where I lived, or where I was raised as a child. I don't know if you can hear any abouts or house or A's, but they're beaten out of me when I moved to the States. But when I go to Minnesota, they think I'm from Minnesota, so I hide. So in Canada, we have been blessed with a lot of uplift in the Rocky Mountains, and near where I grew up, there's a fossil deposit called the Burgess Shale. How many of you have heard of the Burgess Shale? And we'll talk a little bit more about it later. But I was literally hiking near the Burgess Shale. And it occurred to me, and I'd been to artificial life conferences, and I met Chris Langton and later to meet Larry as well. And it occurred to me that the artificial life concept or dream certainly goes far back in history, back to alchemists and way back in time, the artificial being, the artificial human, vivifying matter to dead matter to life. It's an old, ancient concept. But it occurred to me that we needed a new conference on artificial life that was really all about the vision of where the thing's going, rather than about the research and the statistics and the algorithms, etc. And I looked across the mountains and I said, just behind this mountain is the Burgess Shale. And I thought, we should have a conference there at the fossil quarry, because it will be very inspiring to people who have this dream about either trying to figure out where life came from, model early life, the origins of life, model life elsewhere, think about it, or use software as a tool for biology, whatnot. It's very, very cross-disciplinary. And if I could get a group of people who are visionaries but different together, we could climb up to the Burgess Shale. It's only about 3,000 feet of hiking, very easy. As long as we don't come across a grizzly bear on the way, which we didn't. If I could get this group together, we could form something new, which is a visionary movement around the artificial life idea. So we did that. Thanks to the Banff Center in Banff, Alberta, we hosted a conference called Digital Burgess in 1997, and then 3 subsequent ones, which I'll go over briefly. But this is the actual Burgess Shale. It's quite accessible. You can only go up there with a permit, and you can only have 15 people at the shale at one time. We arranged with Des Collins, who's the chief paleontologist at the shale, and his group to come up and be his guests for a period of about 2 to 3 hours. And the Discovery Channel actually came with us, which was great because they captured this event. And the Burgess Shale, there's an interesting story behind it. The Burgess Shale is a phenomenally rare place on the planet. It is a shale which is usually made by deposition of matter on the ocean bottom that is then subsequently compressed very heavily and then subsequently heated. And for the most part, the paleontologists call this shake and bake, where the bake happens and then there's movement in the earth, there's subduction of continental crust, and then maybe it gets pushed back up. There's a lot of shaking. So shales don't preserve much. They're constantly shifting and heating. But in the case of the Burgess Shale, picture this. In roughly about 525 million years ago, North America was tilted on its side, if you can believe that. And the coast, it didn't have the Rocky Mountains. There were some original kind of granite cliffs that you would find in the Canadian Shield that probably are gone or deeply subducted. And there was a granite cliff coming up against the seashore. And just at the right angle, there was a little shelf as the seashore sort of curved into the continental landmass at that time. And on that shelf was a very nice, warm, beautiful environment for life. Now, this is life before life on land. This is sort of that period, that Cambrian period. And it was just at the right place so that there was enormous vitality in the life of those seas. None of it there was no bony structures at that time. So these are sort of soft, squishy things moving around. There was Otoia, there was Anomalocaris with its 13 pairs of flaps and its shrimp-like appendages. These things grew up to about 3 feet long or so, or even longer. And the trilobites, you see, if you go down to Lyme Regis, find all those trilobite sort of stones in the stores, and they're fossils from that period or earlier. Trilobites ruled the world for 800 million years. They're the record holders so far. They didn't survive the mass extinction of the Permian period. But so this is rich environment, and then every once in a while, through sort of subduction or slumping, a whole bunch of these creatures would be carried in a little submarine landslide, and they would go off the edge of this cliff, and they would settle down to a very great depth, probably over 1,000 feet, straight down, black, inky water, anoxic, no oxygen, and they would die there. They would sort of be encased there and die there, and their bodies wouldn't decompose. And these are very soft, think jellyfish or horseshoe crabs. So layer upon layer upon layer of these creatures was laid down. And that wasn't enough. What you had to do then to preserve them, think of the challenge of preserving these very fragile things. So their bodies gradually get flattened out and may make impressions in the layer of mud underneath. But then this whole thing has to be pancaked down quite gently. And you can think of if you were trying to press down some cloths or something with butterflies in between. You wouldn't want to do this. You'd break them up. But you were compressing it down tremendously. I mean, probably 10 to 1 at least, to make the shales. And that happens as the entire thing is pushed down several kilometers under the Earth's surface. And the reason it compresses so cleanly and straight up and down is because of this granite face next to it. So the granite face it's like a single press rather than doing this all the way. So that granite face protects all of that. And then millions of years later, 525 million years later, actually probably 510 million years later, all of this is uplifted into the Rocky Mountains. North America has turned from the equator, is now up this way. A piece of what, we don't know, another piece of Earth's crust comes and crashes into North America and pushes all this material up, forms the Rocky Mountains. Then a spring day in 1905, a man named James Doolittle Walcott is on his horseback. He is the head of the Smithsonian Institution in Washington. He is in the Rocky Mountains in Canada looking for fossils, but he's looking for specific kinds of fossils. Now, this is a really tremendous story. It's one of the legends of paleontology. His horse is going along a trail just below here, trotting along, and his story of it, maybe it got embellished a little bit, was that a boulder suddenly rolled off of a bit of snowfield, tumbled down, his horse stopped, the boulder flipped over just to the right side, and in the sunlight, Walcott could see these shiny slicks all over the boulder that were specific shiny slicks. And so he's one of 5 people who would understand what these little slicks are. He jumps off his horse and goes down and looks and says, "Oh my God, I found them. I found Cambrian creatures. And I found the early creatures I've been looking for." So he trundles up to this location on the mountainside. It's quite steep, but these are Victorian people, even Victorian Americans, big boots on them, and he finds them all over the place. He takes his hammer and knocks them out. And there's another. Oh, there's more. And takes another piece of shale and he's digging and he's trying to get at the face, underneath the talus, and he's finding they're everywhere. Every single little piece. It's an encyclopedia of creatures. It's a mother lode. And so in those years, 1905, in several field seasons, with horses, they pack out tons and tons and tons of these shale fragments back to the Smithsonian and put them in drawers, and it takes several generations for people to get to them. But they're so odd because there were creatures that he found where you could see the clear outlines of the creature. And I should have brought a little bit more detail. This is one that I broke open myself. And inside you can see other little creatures that this one had consumed on its last meal 525 million years ago. So we took a group up to this. This is a great picture. I took this picture. I really like it. This is the archive of the Burgess Shale. This is Tom Ray, who created one of the first simulated sort of biological systems that exhibited properties of, mutation and parasitism.
Hyperparasitism.
Yeah, quite well known in the field. This is Des Collins. Now, this man he's the chief paleontologist for the Burgess Shale, and he's a detective, and he's a world maker. So the conversation they were having was quite interesting. But it actually merged at one point, and the conversation was that Des said, well, it all comes back to algorithms and software, you see, because we take the genetic code of the creatures we're finding here, and we know roughly how quickly these things have been evolving, so we take it back, and we try to find out where the first thing was that was moving along the seafloor that actually could move. The first thing with mouths, and all these features probably were 600 or 700 million years ago, were in the biology, in the biota of the Earth, and it just took this long to branch out. And we're just seeing a slice where we find some of these things, and we're just lucky to find them. There's another site in China that is full of soft-bodied Cambrian creatures. So we spent the next 3 days in the Banff Center, and it's hard to see this, but this is Darrell Anderson with some of his glowing globule bot generations. This is some of Carl Sims' generative art. And we spent the next 3 days talking about the intersection between using software to simulate life forms and the practice of being a detective trying to figure out where life came from. It was just a tremendous meeting. I think you guys can attest. We went on to hold a second conference. This was sponsored by CyberLife and Steve Grand in Cambridge. We thought we'll go from the extant fossils of the Canadian Rockies to the human living fossils of Cambridge. And I'll show an image. But this was a wonderful event because originally Digital Burgess, both Richard Dawkins and Douglas Adams were going to come and climb up the mountain. For him, it was sort of like Mecca in a way. And I had gone to see Stephen Jay Gould, and he really wanted to come to the conference, but his cancer was getting worse and worse, and he said, I can't risk it. When Stephen Jay Gould went to the Burgess Shale, he started to walk down, and he collapsed. His knees gave out. And that's like the worst thing that can happen to you because you're 2,000-3,000 feet from. So Parks Canada's president was in Banff, heard about some guy that needed an airlift, and heard that his name was Stephen Jay Gould, and said, I want to be on that helicopter. So they came and they airlifted Professor Gould off the mountain, and the Parks Canada person was thrilled to talk to him, and they didn't charge him for them. But I actually requested that all somewhat overweight paleontologists, computer scientists, or artists please walk treadmills for a while so you know you can do this hike. And at the end of the hike, I was literally helping one of our paleontologists get, as the sun was setting and people were waiting for the bus, I was helping them down the mountain. I went up and down 3 times trying to get everybody off the mountain because it would have been quite bad if we left somebody. This is Larry Yeager, who's sitting in the front row as the presenter. Chris Langton. So we literally got quite a group together. It was really a tremendous conference. What's interesting, and I'll read an excerpt from the conference, was a speech made by Douglas at this event led Richard to go, the whole thing with the God Delusion. Richard's current work came from this event. And we actually posted Douglas's speech. It's called, Is There an Artificial God? And that caused Richard Dawkins to start thinking in these terms. I'll tell you a little bit more about that later. This was Digital Biota 3 in 1999. We decided to bring real firepower imagination to bear. This is Bruce Sterling and Rudy Rucker. And if you're science fiction fans, both of these writers write about worlds where there are human-created technological beings that reproduces another biology. And that's one of their favorite themes of science fiction. So these people in their minds are already living in a future where there's artificial life. This is some of our sketches saying, could we build some kind of an ego grid? This is a long time ago, but when the web was new. And the last conference that we held, conferences are hard to organize and expensive and whatnot, and I kind of ran out of steam to do them, and you'll see what we did later. Roy Plotnick here, who's a highly regarded paleontologist in Chicago, organized our session at the Paleontological Convention. So we actually held this thing inside where the paleo people were. And it was interesting. It was quite controversial to them because they're detectives. They're not world makers. So it was, how can we help you with this tool to help what you do? And one of the things that a paleontologist came up with, they said trace fossils. And I didn't know what a trace fossil was. A trace fossil is sort of a disturbance in the mud left by a creature. Usually you'll find trace fossils that are much older than any fossilized creature. So they're quite interesting. They're the little ghostly marks of where something's been, but it could be 650 million years old in sediments. And they said, can you help us reconstruct what creature could have made this mark? So that is an interesting application of virtual worlds. Biota went on to do, one of the things I always wanted to do in the organization was to do projects. And we did, the first project we did was called Nerve Garden, and it was a growing L system forest that was grown in front of the public, by the public, who extruded their own L system plants and then put them on these islands at the SIGGRAPH conference in Los Angeles. It was a tremendously fun thing. So the idea was to get the public involved in creating a simulated, biologically inspired world. We morphed the organization, and you're all most welcome if you like this kind of discussion. Please come to the site because we have a podcast, and that means audio, a tremendous amount of audio. There's audio of all the speakers of the original conferences, plus interviews and a weekly radio program that you can call into and be part of, as Justin's been several times. So that is what Biota has morphed into today, is this channel of communication about this idea. What is artificial life? Well, believe it or not, I'm digging around trying to find the origins of this idea in software and in computers, and for the next couple of years I have a visitor's appointment at a place called the Institute for Advanced Studies. It's in Princeton. It's not the university, but it's next to the university. And I was reading around in the histories of the Institute, and the Institute's famous for many things. But one of the things it's most famous for is really the invention of the modern computer, because that is where von Neumann was after World War II to build the von Neumann computer architecture. And for you computer history buffs, I mean, I'm a real history buff. I have a big collection of old computers. This guy von Neumann goes into an institute where there's never been a laboratory. They don't do this kind of thing. It's all about study. There's a department of there's economists and mathematicians and everything. There's no discipline which needs a laboratory. They have no students, everything. It's all about study. And he sets up, without really full permission, he sets up this workshop to build this vacuum tube machine using the highest technology of the day to create the best computer architecture for the world. And the IAS are going, oh dear, they're at it again. At least the building was somewhat far. It's where the kindergarten is. The play school is right there. And, oh dear, what are they doing? There's all this banging going on, disturbing our study. But over a period of 3 years, von Neumann, what he did, and we owe the modern world to him, he made the first modern computer which had registers and memory and buses, and he designed all that, and every quarter he published reports about it. He gave the reports away, sent them to any institution that would want them. It's an open source idea. Take it. And everybody who was at UCLA or Harvard or whatever in the UK, people are trying to create a computer for their institution, kept getting these reports which were so far ahead in thinking of anything that they were doing internally that they just said, just copy this. This guy's obviously ahead of us. Why reinvent? This is the better wheel. And that's why you have the von Neumann architecture now. That's why you have all these computers that pretty much work the same. It came out of. But in the 1948-49, there was a fellow named Boricelli at IAS, and he was waiting for the von Neumann machine to be ready and done, because he had an idea of the first big scientific application for it, and it was artificial life. He called it numerical symbioorganisms. And you can imagine on a machine with it was actually a very good performing machine, but with so limited capacity, he put these strings, very much like Tierra, ran replication algorithms and whatnot. So I was fascinated by this. And it took up everything that the IIS machine could throw at it. And it worked. And there were reports about it and whatnot. But it really was the first scientific computing application, was an artificial life application on the first computer of the modern age. Interesting history. Later on, all of this was sort of rediscovered several times. Or redone. There was Conway's Game of Life from the 1960s, which were patterns on the sort of cells and adjacent cells and patterns to be. They were a very popular game into the 70s on microcomputers. In the 80s, Chris Langton was fiddling around with Apple II software, and several other people. There's a history is too long to describe, but an institute was founded. This is the Santa Fe Institute up on a hilltop, eventually up on a hilltop in Santa Fe, and this thinking all coalesced, and tremendous things came out in that period, very productive period. What I want to do now is to show you what you're going to see is one of the things that I saw that really convinced me there was something here. And this is work done by Carl Sims in the late 80s and early 90s on the connection machine. And the connection machine was this, I don't know if many of you remember, it was this black cube, about this high, this wide. It had, I think, up to 2,000 processors in it, very small processors, massively parallel machine. It was built by a company called Thinking Machines. It's a great name, especially for that time when there was a lot of interest in artificial intelligence. Danny Hillis formed the company, hired this young guy, I guess he was at MIT at the time, called Carl Sims, and said to Carl, do something interesting with this that shows why you need such a powerful parallel machine. And Danny had been a biologist. I guess he'd been trained part of his career as a biologist, and he was interested in biological simulations.
But these creatures are the result of an astounding new idea that may soon take us from the...
And this program was produced around 1994, Scientific American Frontiers. And I'll explain kind of what you're looking at a little bit more, but this is a very good short piece. So what you'll see and what Carl Sims did was he took these 2,000 processors, and the idea was, what can you do with them? What can you do with them that you can't do with just a single processor box? And he was thinking, because Danny Hillis was a biologist, he was thinking, all right, I've got to think of something biological. And then he thought, why don't we see if we can make simulated evolution? Because we can then have an individual creature, simulated creature using an individual processor. And use them up. This actually turns out to be an interesting theme later. And so we'll create a very, very simple genome. And what he does is he starts out with, says, well, I don't want something that's all numbers, like Tierra or like the symbioorganisms of Boricelli. I want something that's very visual. So I'm going to create a little physics world. The creatures are going to be made out of blocks. And I'll start with a hinged block creature. And I'll see if somehow the way the creature reproduces its limbs and changes the shape of it that it can interact with a simulated fluid. So two hinged blocks don't do too much in fluid, but when you get a third one, you get kind of a tail whipping effect. So he said, if I can only get this creature to have a genome that will, for some of the creatures, generate a third block, which will give it a tail motion, I'll get motion. Then I should be able to set up those creatures in a biological simulation. And he did it, and it worked. And literally in a period of weeks, he not only had creatures sort of swimming through water and evolving different strategies. There were ones that had 4 paddles. After thousands of generations, there were ones that would move like a snake. But then he turned gravity on, and they all fell to the ground, or at least the best swimmers. And then they couldn't, with gravity, they couldn't deal with it. But with this same kind of culling algorithm, gradually the now fish out of water became better at walking. And there were even contests where he would have the creatures try to get at a green block. So they would start from one position, they would move around and get to the green block, get control of it. And if one got control of the block, it would reproduce. And so over time there was incredible strategies. One creature would come around with this arm and then pull the block toward it and move it away like a crab. There were other creatures that would, and the winner, actually the speed king, and you see this in university courses, engineering courses, where they have the robots come and try and get as many ping pong balls as possible, competing with another student team's robots. The winner of all was this creature that just simply put this paddle out of this block and slammed it down on the cube, and it didn't matter what anything else did, they couldn't get control of the block. And that was the all-time winner after many generations. So you'll see some of this in the movie. But whenever I show this, it really communicates to the public what this is about. It's very, very anthropomorphic, if you will. People are rooting for these creatures.
Superintelligence. Robots like Flaky must be programmed feature by feature, but not these strange things. They created themselves through a process called artificial evolution. Evolution, by itself,
has led to the creation of incredible complexity. Ourselves, all the organisms in the world. This process happened on its own, at least in my opinion. There's nobody that assembled all of these wonderful things in the world. On computers, we can simulate the same process, and we can get these very complicated, very interesting things without having to understand them and assemble them.
When he first dreamed up this evolution idea, Carl Sims couldn't predict what would happen. He just gave his computer some basic parts and let his creatures go from there.
The bodies of these creatures are fairly simple. They're just made of some number of blocks. The blocks are connected by joints, which can bend or twist. The creatures also have a nervous system. They have sensors, which can sense the angle of the joints or sense contact. And the nervous system processes the signals from the sensors and tells the muscles when to move, which generates some kind of behavior. I've given it the capabilities to include all of these elements, but the computer actually decides how they're assembled and how they're used in specific creatures.
Numbers chosen randomly by the computer, the synthetic genetic code, described how the first simple creature would look and how its nervous system would be wired. Then it was put into a simulated lake and told to swim. It twitched, but it didn't get anywhere. So now the computer went to work. Using the original numbers as its base, the computer made a few random changes, the equivalent of mutations. It did this again and again, creating a new generation of 300 different offspring. Then all the offspring got a swimming test, with the best swimmers selected as the basis for the next generation.
When the computer makes mutations in the genes of these creatures, it has no idea what these mutations are going to do. Sometimes the mutations might knock out a piece of the nervous system and perhaps cause the muscles not to move anymore. But other mutations might actually improve the motion.
So from the original creature, increasingly better swimmers evolved over generations. all without any human intervention. In the end, this was the best swimmer of all. But when Carl Sims put it on simulated land, it was like a fish out of water. So, over subsequent generations, the mutation and selection process had a new goal: to walk. After 15 generations, this was the champion. Other computer runs have produced even better walkers.
Sometimes these evolving creatures would think of solutions to their goal, which were completely different than I expected. In this one example, the creatures got taller and taller and taller and would simply fall over. Instead of figuring out some clever way of walking, they would fall to generate horizontal velocity. What I was telling them to do was to just move, and falling was a perfectly good solution as far as they're concerned. So this creature specialized in falling for as long as it possibly could, including doing a complete somersault.
The strength of artificial evolution is that it comes up with solutions that computer programmers could never imagine.
Isn't that cool? What Carl Sims showed was that you could, through this really relatively simple culling algorithm, what's happening is this genome, which is what's called a directed graph, and what it's doing is it's cutting out and putting in and cutting out, putting in, and then you're taking all of these variants so that the little directed graph is now morphed, and the directed graph creates a different creature, but a slight variation on the creature. And then you're putting it into the test: swimming, walking, competing for food, following a cursor. And then that test is automatically picking the next creature, which is then morphed again. And on a connection machine, it would only take them a few days to come up with all these forms. And what was interesting was I was at the Santa Fe Institute in 1994, and they were just getting the Mosaic web browser working in Chris Langton's lab. And I saw the first one of the first websites they went to was Carl Sims' website. So I saw this strange thing, and it was actually they were playing with the fossil records of Carl Sims creatures, because it was only MPEG files, and by that time Thinking Machines was close to being out of business, and so there would be no more big black cubes, maybe a few of them running. If anyone sees one on the street, call me up because I want one for my computer collection. But that machine was going away. And so on the web came these MPEG files that people were playing on a web browser. And that was a fossil. I realized I'm not watching a live thing going on, I'm watching a fossil. But that fossil was so inspiring that I got in touch with Carl Sims as Thinking Machines was closing its doors and said, can I take these out? I can break into Thinking Machines' website and I can get these MPEG files out, and can I rehost them for another generation? He said, sure, I can't do anything. The company's going out of business in Chapter 11 bankruptcy or something. So I busted into Thinking Machines, took out the fossils, and built a website to show this, because this is just too important not to preserve. And that actually did lead eventually, because otherwise that would have been lost. You would have seen a SIGGRAPH paper with an image. Those MPEG files were what was needed to keep a new generation inspired. And so we did that, and that was one of the first projects we did with Biota. And then Carl Sims came to the Digital Birdist conference. So I'm going to turn the sound off since we don't need it. So Carl Sims, that was an early example. Larry Ager created Polyworld. What year was Polyworld?
About 1990 to 92.
1992 on silicon graphics machine. And Polyworld, would you give us a brief description of Polyworld?
The main thing that evolves in Polyworld, unlike Carl's, where the body morphology and the sort of embedded control structures are what evolve, I tried to make mine based on our best understanding of simple neural models, and so they are summing and squashing neurons that do heavy learning at the synapses, and the main thing that evolves is the wiring diagram of their little brains, the neural architectures. And then they have to survive and reproduce in an ecology.
So Polyworld, you open source Polyworld
Yes,
some years ago.
it's on SourceForge.
So Polyworld is a living fossil, and several people I think have taken it and are taking it further. What I was going to show you is that there's a whole new boom in artificial life. By the late 90s, there had been a hype, as the media often does, they hype the field up, and they had hyped up the artificial life field. And Chris Langton, toward the end of the 90s, I got him involved in avatar worlds. When I went to the Santa Fe Institute in 1994, I was bubbling up with this possibility that there would one day be avatar worlds on the net. And it was great pride that I got him addicted to this 2 years later. And he was in active worlds as an avatar talking about motorcycles, 5 hours a day. Didn't contribute to his career much. But what I wanted him to see was that the virtual world space represented by what is now, say, Second Life, could be a space where you could do artificial life experiments. I've since come to the conclusion that's not the case for a number of reasons. But in the late 90s and into the 2000s, there was a whole new generation of people, some of whom found Carl Sim's MPEG movies that you just saw. They started their own little artificial life projects. One of them was Tom Barbalet in Australia. They generally work in a garret alone, building, and these are mostly men because women can already reproduce and create life. No. As Galen, my wife, who's sitting right over here, he's vanished. Oh, there, she said, why are you so infatuated with this? We women know that life is created one peanut butter sandwich at a time. So, anyway, what happened was there was this bubbling up of enthusiasm with artificial life. And I thought, before the same thing happens to these folks that happened before, we can use a new tool for them. And the new tool is called the internet. Because the first generation of artificial life really didn't use it that much. Because you needed quite powerful machines to make these things work, from connection machines to silicon graphics. And there was only a rudimentary use of the internet in, say, Tierra. But these guys were growing up in the era of Web 2.0 and Ajax and social networks and all this sort of stuff. Everything's interconnected. So about a year ago, I came up with this thought of sort of a vision of there's a simulated forest growth world that's being built in University of Paris. It's called Darwin's Park. And it's kind of, what's great is it's sort of like where we left off with Nerve Garden, where you saw people growing those plants and sticking them in the islands. Darwin's Park is like the full-on plant simulator. Plants can shade other plants that then grow differently. Underneath the soil, the roots are moving along pathways of minerals and water that's simulated under the soil. And they're actually going to be using this for real agricultural productivity studies. It's really cool. And one of the comments of Claude Latour, who created this thing, was, gee, we'd like to have some creatures in here because plants interact with insects a lot of the time, leaf cutter ants and things like that. And that's really part of agricultural productivity. But we don't have the resources to do ants. We don't do ants. And then there's this fellow, Brian in Boston, in the GreyThumb group, who does have an ant simulator. Is it Brian or is it Adam? Brian. And it occurred to me that, well, what if Brian's ants could somehow be packaged up in XML in a little capsule, and they could wander through the semantic web and pop up into Claude's forest world. And they would be sort of, think of the Matrix, when they're going in that funny glowing craft and then the robotic world, but the humans are preserved and they're going to alien environments and they go other places. The ants are arriving. Now, of course, the ants arrive in Claude's plant world and there's no gravity. So they go poof out of their XML capsule, and then they're floating and they're saying, we're ants, we need gravity, give us gravity. So Claude's team would have to code in gravity and the ants would drop to the ground, and then they're moving along, and then Claude's team would very quickly say, well, they need to interact with the plants. They need to know the difference between the geometry that's a leaf of a plant or the ground, because they want to dig in the ground, but they want to cut the leaves on the plants. So we have to create all these what are called affordances or APIs between ants and plants. But this would really inspire both Brian and his ant simulation, because there would be a user of the simulation. It would inspire the plant people, saying, we just got something better than the sum of the parts. We can go to our funders and get more grants. We might be able to hire Brian to extend his ant simulation. And this is called the grid effect. And this is what dominates big computing now. Artificial life, World of Warcraft, whatever, Google, it's all on grids of machines that are communicating and cooperating. The supercomputing projects, everything. So my mission was to bring the grid to artificial life and see what happens. And so this is actually an idea that seems to have gotten, and I can't write it. I haven't written a line of code in 15 years or so. I don't know if you have the same problem. You're still doing it? Oh, you're lucky guy. It's so creative. So bring the grid to artificial life. And when you think of it as it expands, you know the network effect. The network effect is, if you have one fax machine, it's worth nothing. If you have two, they're kind of useful. But if you have 2 million, they're really useful. And so the whole goal would be to have all kinds of artificial life simulators that are sending objects back and forth. Now, some of it will become really nonsensical, because some of the simulators are they're purely numerical. Some of the simulators have a 3D geometry and physics. Some of them are like for fishes, and others are for plants and structures. So in the beginning, it will be kind of a hodgepodge. But I think a combination of these things arriving in your world and not knowing what to do with them, and there will be something that's beyond what the programmers can conceive, which is there will be all of these autonomous lights out interactions that will go on, because objects will arrive in your world and they'll cause all this bizarre chaos. You might come and find your entire planet world is mowed down by something that came through. And this thing that is mowing plants down is now going into other artificial life simulations, and it's interacting and it's doing other crazy things. And then the plant simulations, because it's a feedback loop, because there's a genome, because there is an energy cost equation, the next time the thing comes in the plant world, it's harder for it to mow them all down. Either they're growing really quickly. The plants learn that if they grow ultra fast, they lower the frame rate so much that the creature moves on. But you'll see all these bizarre effects happening that aren't programmed by anybody, which is what we learned from Carl Sims here, but on a mass scale all over the net. So that would be pretty cool. The problem, of course, with all that is it's really, the environments are quite different. So somebody's paramecium simulation is at the wrong scale for the plant simulation. And there's one other issue with it, is it will create all these really interesting emergent properties, but does it tell us anything about the origin of life or biology? And a biologist might say, all very interesting, it's a simulacrum, or it's a facsimile of what we see in nature, but it isn't nature. It tells us more about the cleverness of the programmers and the strangeness of mass effects and emergence in software networks than it does about life on Earth or a future of life. So in order to go deeper, the EvoGrid, so I realized about 4 months ago that the EvoGrid project really has two flavors, if you will, two flavors of EvoGrid ice cream. One is broad, where connect any simulator to any other simulator and hurl things back and forth and see what happens. And that's a broad thing, and that might teach us some lessons, but there's a deep version. And the deep version came out of I'm writing a book chapter for a large book that's coming out in October. It's called something like Divine Intervention, Natural Action. And it's 30 authors, look for it, from World Scientific Press, 30 authors, including a cardinal from Rome, 2 rabbis, the head of the Vatican Observatory, an evangelical several evangelical thinkers, biologists, sociologists, philosophers, and I'm the only nerd in there. So I read about artificial life. The chapter that I wrote, and it took me months to write this chapter, to write about 10 pages. I kept getting into these logical loops. Because my thesis was, if you make the strong claim that God is an intelligent designer, therefore God has a design for the universe and is always tweaking and poking things along the way to make them happen, then God has to be observable. You should be able to either find a God detector in nature or build a God detector. So the chapter is called The God Detector. And if you'll permit me, now that I'm not burdened with any individuals, the God detector idea, it's a little bit of a joke, but it comes down to this. If you actually whittle the universe down into its basic components, not that I can do this, but it just sort of seems common sense. It seems like there's natural laws, and it seems like there's randomness that can't be modeled. It's just Murphy's Law, or it's random numbers, or it's Brownian motion, or something. That's one of the things that feeds the universe. But there's a third thing, and it's copying. And you live in the copying universe. Everything in this room that isn't sort of made by natural laws and whatnot is a copy of something made from a blueprint. These chairs, the words I'm speaking, the culture, language are copied from brain to brain as we learn our language and we read things. The cells in your body, the cells in the wood in these walls, it's all a result of copying. And for some wonderful reason, our universe, with the parameters that it has, in little tiny areas of the universe, just like the little tiny areas of the Burgess Shale that were preserved, copying is permitted. Because certainly inside the sun, there's no copying. It's just complete, thermodynamic chaos. You can't observe copying in many places. We haven't found anything copying itself on Mars yet. Rocks don't copy rocks from a blueprint and make another rock with slight variations. So copying is rare. So if God was tinkering with the mechanism of the universe on an ongoing basis, God wouldn't really be interested in Mars at the moment, because there's just a bunch of rocks. It's not interesting for a God. No one to talk to, no one to believe in you. So God would only be kind of involved in the universe where there was copying going on, which is where we are right now, where organisms are. So then you say, all right, if God can actually affect natural laws and isn't interested in those regions, God certainly can't affect random. Random defeats everything. Otherwise it wouldn't be random, it would be a natural law. Then God has to affect the copying process. And in this chapter, I'll save the suspense. You'll have to buy this book. I'm supposed to be promoting it for World Scientific, but it's God could affect copying before it starts with the inputs, during the copying process, or on the output side. And what I show in this book is that for God to predictively know exactly how to affect copying, i.e. change the random mutations, God's brain would have to be bigger than all the countable particles in the universe. Therefore, God couldn't exist inside the universe. It would have to be outside. Therefore, God is omnipotent and outside the universe, and there's no debates. All right, that's the end of the debate. It means I'll not write a book like that. But what I showed, I think, in the chapter was that God probably can't affect the individual copying that's going on, because you can't do enough predictive calculations to make it happen just right every time. But on the output side, where there's like an error, God could be there adapting to the results of the copy. So the example I gave was when the Hebrew Bible was translated into Greek, they made a copying error, which was very significant. The Greek translators changed the word for young girl in Hebrew to virgin in Greek. And probably there were several copies of those texts that were translated. Maybe there were ones not translated quite the same way. But it turns out that in the Eastern Mediterranean there was a whole religious tradition of virgin births. It wasn't in the Hebrew, but it's now in the Greek. And probably the chief scribe monk said, hey, it's a good idea. It'll help us be more acceptable, because we're a struggling young movement. And so it stayed in, and it had a profound change on Christianity. There's evidence that in the early Gnostic Christian church, women were pretty much they were equal. They had equal roles. And that change, that was certainly, that one change shifted, made celibate monks, it made nunneries, it actually probably pushed women's role right out of the church, was one of the contributing factors. So these mutations within script certainly have a powerful impact. But if you say, well, then God was affecting the monks' decisions to keep the errors in, it comes back to this uncountability problem again, because then God would have to know all of the neural brain patterns and affect all the neurons to go to the chief monk's brain and say, that's a good idea, keep that. And again, it becomes an implausible thing. So perhaps that God is an intelligent adapter not an intelligent designer. Therefore, God is no different than natural selection or our intelligence, which does adaptation. When things don't go quite the way we want, we adapt. So that's this particular book. I hope you like it if you get a copy, but I'll have my chapter posted online. But that's a little bit of a diversion. The fundamental question is, what is artificial life about? What can it do for humanity? What can it do for science or for philosophy? If for instance, one of the things in the artificial life community is people who believe in creationists and intelligent design look at artificial life and say, see, people are making those algorithms. People are intelligent, therefore God, by tweaking and making the algorithms, is also an intelligent designer. So that's the big debate. But I would suggest that there's something more fundamental. That none of that matters at all, because it's just creative programming. It's clever programming. What matters is something deeper, which is, could you start at what Richard Gordon calls the origin of artificial life? So origin of life we think of as there's the earth, there's the oceans, and there's no life in it. And suddenly, or over a long period of time, small vacuoles that may be forming naturally in the water, or maybe at the waves at the seashore. These vacuoles, you can actually study these as oceans, water waves break on the shore. They form these little, I think they're bilipid vacuoles or something. One of the theories of the origins of life is these little vessels are forming and being broken up constantly. What if one of them formed around a bunch of cellular machinery, and that cellular machinery was good enough that it just at the right time patching a hole in the wall of the vessel so that it didn't get broken up? That wouldn't be enough for life, because now you've got this vessel floating around with a little piece of cellular machinery which is constantly sending out repair mechanisms that keep this balloon together. Don't let the balloon break. And then ultimately it breaks. But what if eventually there's a longer string that is really able to keep the balloon intact for long periods of time? Well, for a cell, we know that every cell in your body is a balloon full of seawater, pretty much, and it's got mechanisms to keep the membrane from being disturbed, and actually for all kinds of nasty things coming in through the membrane too. It's very complex. That's your field, Rachel. But the jump between that little vacuole which may have existed and the little repair mechanism and this thing called the eukaryotic or prokaryotic cell, which is an amazingly huge machine. It's a machine that you can't model it with a supercomputer. There's so much going on inside there. And it's got a blueprint that it's working off. It's got factories making proteins. It's got things making energy. It's a whole city in there. It's a refinery complex. And its whole job is much more grand than the original vacuole. It not only maintains the cell wall, it maintains what can come in and what can come out. It generates energy. It could move. It does the most miraculous thing in that it one day decides, I'm going to make a copy of the blueprints, and then I'm going to pucker the wall in. I'm going to split off the blueprints and all the elements and make two of me. And it's that jump probably that was where life came from. So my challenge for the artificial life community is do an origin of artificial life experiment. And this came from Richard Gordon's chapter in the same book that's coming out in October. What if you started with a soup, huge particle simulator, basic physics, and you ran millions of computers onto this soup, and the soup really could be a mathematical analog of the chemistry of the oceans or something. It wouldn't be an attempt to simulate that chemistry. It would be impossible to do. But it was a mathematical analog. So some of the particles attract. Some of them, they're all affected by sort of disturbances through the medium, which come every once in a while in some way. Some of the particles bond in certain ways, so you can be mathematically like properties in chemistry. And if you ran this, would you get molecules that would copy each other? Probably. This has been seen before. You can do it in raw bathtub chemistry. You can do that. Could you get vacuoles that would form that you understand are containing other particles? Possibly. But could you go that final step of the machinery of the preservation of the vacuole, the making of things from blueprints, and the reproduction of those bubbles? And I posit that would be a more interesting challenge than many of the things we could do in this century, and maybe that computing itself came upon our species, so we could do a grand experiment like this. Before he died, Douglas Adams did this tremendous speech at Digital Biota 2. He died of a heart attack, I think, in 99 or 2000, shortly after the conference, which was a real loss. But he talked about, the speech was on artificial God, and he talked about that computers are tools to understand the whole universe and to simulate the universe and to simulate life in the universe, and so we can understand where we come from. So what more noble goal to say to a computing grid or a community, let's try to see if we can, in an abstract way, in principle show how from nothing, our abstract mathematical nothing, something comes. Now, when you get duplicating bubbles with complex machinery inside, what do we have? What responsibility do we have as a species? Say that started to happen. Say it was like SETI at home. How many of you ran SETI at home? SETI at home was this great environment where I think it was all based on Arecibo telescope data, but they would be scanning the skies for signals, and you would log on and install a screensaver. And the screensaver would simply go out and grab a chunk of the data from the SETI at home server and pull it in and look for patterns and report back. And so there were probably 2-3 million machines in SETI at home. This is about 10 years ago, and it's the model for these distributed grids. But what if you had a Biota or whatever your evil grid set up like SETI at home? Well, your little computer at home would be going out and grabbing a frame of the particle soup, pulling it in, and running the math for the frame, and then replacing the frame. And the next frame was being run by somebody else, and nothing could happen until all the frames are put back into the simulation, and then suddenly the clock goes, and everyone else can now go grab a new frame. And we know with computing architectures it's possible to do this. And the prize would be that in your computer at home, the first EvoGrid authentic reproducible machine in the container object would appear, and the light would flash. Bulb would flash as you're the winner. You after all this 10 years of computing or 2 weeks of computing, you're the machine that did the thing. I mean, you didn't do anything really, just left your machine on overnight. But that would be an interesting outcome. Then they could, if that happened, they'll stop the simulation. We're going to go and probe this because no one's watching this, no one's manipulating this. You might run it for a few more frames because if that thing didn't persist, it didn't pass the test. It has to persist. That line of things has to persist. Every ancestor that you possess back to 4 billion years, 3.8 billion years, survived. So the smallest single-celled organism to the swimming notochord thingamajig in the Burgess Shale, they're all your ancestors. They all lived and reproduced. They belong to you. So you have to actually have continuity in these EvoGrid objects. So if you run it a few more cycles, and it's very much like how they do prize competitions, where you can break the sound barrier in thrust 2 on the Nevada desert. You have to go through it, and you have to hear the sonic boom, but you have to turn around and go through it again in case the wind did something. So there's always like 2 flights of Spaceship One in 2 weeks. Test it again, and then suddenly the world knows that this test has been passed. Well, what does it mean? It means that our species will actually have a whole lot of questions to ask, and some of you in the audience are better prepared to ask these questions. But if in principle we've shown that life can emerge from non-life, it's a big moment, a very big moment. Now, this is only in a simulator, right? Well, how different is a simulator from matter? If you read Seth Lloyd's book, Programming the Universe, which is a great book, he's a quantum computing guy at MIT, he says, look, at the quantum level, forget about atoms and hard bodies and suns and stars. It's just a quantum qubit information grid. So the quantum qubit information grid is underneath everything. And there's no particular pattern that would show you you're inside of a star, maybe, versus inside of a human heart. It's the same kind of stuff that's going on. It's this furious algorithms are running. This is his theory about the universe. So if you took your quantum bit microscope and pointed it over your finger, you'd see a bunch of quantum bits. And if you pointed it over a star or what you thought was a vacuum of space with nothing in it, you'd see a whole bunch of activity. And if you pointed it over a computer running an EvoGrid simulation, you'd see a bunch of furious activity. There's no difference at that level at all. The activity would be slightly different because the algorithms are executing different things, but there really isn't a difference. So at that level, is the EvoGrid creature alive really? Is it an origin of life event? As far as at the quantum level. Now, we know we can pull the plugs out of the server and it's all over with. We might get, it might have been classified as an endangered species, so we'd be in a lot of trouble by that point. So that's one level, one layer to ask. There's another really interesting philosophical question. If you step back even further and you say, well, our species with 10 digits, here's the early Earth, Anomalocaris swimming through the oceans, and you've got trilobites. It's a happy world. And in comes an asteroid right from the South Pole, slamming. It was a big one. It's 20 kilometers probably. I know this because I work with people who are trying to save the Earth from asteroids. Rusty Schweikart. We're doing a project showing how a spacecraft orbiting along the front of it can gradually change its orbit over several years. A robotic spacecraft. We got to deliver this on Tuesday. So this is in my head. So these asteroids come in, the Permian extinction, blasted Antarctica, huge amount of debris. The trilobites, these things from Lyme Regis that you see, all extinct. Can you imagine the power of that impact? Because it pretty much must have boiled the oceans off to get those guys that are all living in the ocean bottom. So they're all gone. Dinosaurs, 65 million years ago, impact in Mexico, what is now Mexico. Dinosaurs are gone. Mammals are there. As each event occurs, you get more sophisticated beings that can survive that and come back. Dinosaurs were a certain mentality. Perhaps they would never have developed technology. Well, mammals did. We may have an impactor coming yet. If nature decides, these buggers aren't going to do the job. Let's try the last time with cockroaches or something. But you might consider that if there was a sort of overall weird Gaian logic to all this, what is the purpose of having a biosphere? What is the purpose of life filling up a biosphere and trying all these experiments? Evolutionary experiments, survival from catastrophe, fill all the niches, create a super species like us that kills a lot of other species and changes the atmosphere. We're all part of something. And is it that we're part of life trying to continue beyond the single bubble that is the Earth? The single bubble there, and it's pretty fragile, and it has a short lifespan. They think now that we have about 500 million years left before it's too hot for plant life on land, and that's not global warming. It says that the sun's temperature has been going up very constantly. It's a very stable star, but it's getting hotter and hotter. And after 500 million years, the whole land masses will be deserts, baking deserts. So everything's back to just ocean for large things, and then something like 2 billion years from now or 3 billion years, the oceans start to boil away. And then you don't have any chance. Then you've got bacteria living in the crust until the sun gobbles up the Earth and the sun turns into a red giant. So these little bubbles have a limited lifespan. So if the whole bubble wants to reproduce, just like the cell or the bubble in the ocean, what does it got to do? What does it got to do to mitose? It's got to create some kind of giant blueprint, a giant copying mechanism, and a way to do the copying, and then a way to create another biosphere. And if you read, I think it's Dorian Sagan's writings, he's got a book called Biospheres about that. But I propose a very wild and weird theory that human beings are a massive copying mechanism. We really do it well. We sell a lot of Big Macs, and we do a lot of financial bubbles. We're good at those. Destroy our mortgage market, and then we'll destroy the stock market. We're really good bubble makers. We're good at information. We're good at copying. We copy ourselves. We copy our information. We're really good at it. We're trying to extend our lives so we can persist more into the future. The blueprint, if you will, that has emerged that is new that isn't biology is technology. Giant blueprint. The internet is here. It sucks up every last brain cell we have. It sucks all our time, right? Is there something going on here? Emails 4 hours a day, 6 hours a day, World of Warcraft, texting. Our brains are being sucked into this giant copying mechanism, at least a socio-economic, cultural copying mechanism. If the Earth as a whole was saying, I got to get this job done, I got to make another Earth somehow, or I got to make another form of life, we're a pretty powerful tool to do it. We're a pretty unreliable tool. But we may be evolved, we may exist to do this job. And this is kind of an odd theory, but how would this work? Well, the Earth copying or the Gaian copying mechanism figured out, okay, they got 10 fingers. We gave them 10 fingers, gives them a good numbering system. They're crazy about making money, so they're going to be into information, copying numbers down. They're numbers creatures. They've got binocular vision, so they see depth. Let's see, what are the other properties? They have short lifespans, so they work furiously. They don't take it easy. They got mortgages to pay, so they're going to stay at the job. And they're furious about making tech. They're fascinated with tools, and they're mesmerized by 3D environments and by visuals. So the natural thing is for them to invent an information mechanism that's very visual, to suck them into World of Warcraft, Second Life, whatnot, internet, and use every brain cycle you can. And perhaps the mechanism's probing around saying, okay, I created you, the copying mechanism, I created the copying matrix, now figure out how to do copying and copy this civilization. So it'd be like you could wear a t-shirt saying copy this planet, or copy this biota. And that some odd version of humanity decides to tackle this origin of life problem using computer software, and manages to show that computer software can show that you could have life arise from non-life. Well, there's sort of I'm just sort of working out this in my head as I'm going here. You can probably help me. If life is at all aware and conscious, which we can never know, the life that you might call God, the intelligent adapter might say, bonkers, they did it. They figured out that they can create life from nothing. Let's go a little bit further. Let's pour all our energy into the thing that they just did. They're going to be fascinated by it. They're going to put it in video games. They're going to do, etc. It's going to grow and grow and grow in complexity until you have this massively complex matrix of quote-unquote not really living things, but boy, they look like biology. And Richard Dawkins, I'll go and have tea with him again and say, I promised you, this is in 2001, I went up to see him in Oxford. I probably can't get an appointment with him now. But he said, I'm really interested in this idea of artificial life across the internet. Count me in, I'll look at it. I'd go back to Richard Dawkins and I'll say, open the laptop and say, look at this. As a biologist, he'd say, oh, okay, it's more simulated artificial life, but it's really interesting. Oh, look what it's doing. I'm going to study this. I'm a biologist. I see patterns. I see the patterns of living things in there. I'm not going to call it a living thing because it's too controversial, but I'm going to study it nonetheless. So that might be an important moment, but think of it this way. How does life get off the Earth? One way is to take the space shuttle or to go with Mr. Branson, Sir Branson. That's it. The problem is, whether you're going with Sir Richard or NASA or Space Adventures in Russia, and I know this because I worked with the space agency for 10 years, you get up into orbit, it's lovely, you're in the space station, you're floating around, you need constant resupply. 5 more minutes. And it's a very fragile environment. You're basically inside of Isambard Kingdom Brunel's creation. Isambard Kingdom Brunel, as you know here in London, was the great engineer who created the steamships and whatnot. The space shuttle and space station are nothing different than pressure vessels that IKB would have seen and said, oh, that's a pressure vessel. And you're going to have problems with those seals. And the space station can't survive for more than a few months without something going wrong. It's a constant maintenance. In order for us to actually live off of the Earth as a species, we need things that aren't hard parts. We need living ships. And in truth, we can't, as a species, go anywhere that there isn't life already. That's why when you go to Antarctica, every hamburger and everything to drink except for the frozen ice water is moved in by aircraft. It is a completely non-habitable place for humans. It's a lot like the moon would be. So you actually have to, if we're as a species or as a planet going to go out from the one bubble we're in, you need to actually engineer and evolve things that can live off the planet. Freeman Dyson came up with a thought experiment called, he's at the Institute for Advanced Study, he came up with Dyson's trees, these things that would be engineered by people but would live on comets, icy objects, all throughout the solar system, because there's lots more surface area on comets and asteroids than there is on planets. If you could evolve things that would live, it'd be like fuzz, it'd be like bread fuzz, around comets, growing very slowly because it's very cold. If the whole solar system was full of a biota that was from the Earth but evolved to live in space, we could then go out there and say, hello, fuzz, can you give us a little bit of air if we process a few of them down? And there are our life support system. Because you couldn't have colonized any of the continents without life support systems from biology. So that's kind of reaching the end of this non-PowerPoint enabled stream of consciousness, is that maybe this whole exercise, it's about sort of our fascination with our origins and our future in the universe, or just plain fun, alchemical fun, but maybe it's a bigger thing that's about life itself trying to procreate, and that we are a mechanism and the technology is a replicator, a way to do that. And as Jeff Goldblum says in Jurassic Park, life will find a way out. So and I hope you've been able to follow this to at least some part of it. But that's just kind of this will be a basis for my PhD work with Elizabeth and crew over there. And it will be mainly a philosophical work.
Duration limit for the minimum number of participants. The system may close the conference.
Closing the conference.
If you wish to remain in conference.
That's a good sign. See, the guy in biology is telling us we're through. So I think we have some.
Thanks very much for speaking.
Question.
It's not so much a question, it's really a response. I think you're taking on a huge thing with artificial life, trying to say, is this like nature? Because I still have a problem accepting your leap from somebody putting in some parameters into, albeit a very sophisticated machine that can create of its own further beings, to say that's really a simulation of life that can be close enough to what happens in nature. I feel that's a very big jump. I think it's attractive. I would be willing to play with it and participate, but I would still have reservations because the beginning of it is still a set of parameters decided by ourselves. But what I was wondering is, can one also use this tool for perhaps more modest tasks which have a practical application somewhere, so that rather than taking on life, the universe, creation, one could also say, well, let's test the usability of this in a smaller segment of life. I can't think of an example at the moment. I think it's a fascinating idea, but I'm filled with doubt about the acceptability of matching these ideas. But
I completely agree with you that if we created a primordial soup, no matter, and the question is, if you're putting in the parameters, but you're not touching it, it's lights out, it's still artifice. But I think, in a sense, it's reaching back far enough that it's becoming interesting. It's interesting artifice. Now, so that may be just enough. I mean, it's certainly, it's as big a thing as I could do in a lifetime. Probably won't see it in my lifetime, but some really good examples of this. NASA and some of our projects on going to asteroids, I designed a way by which crews could do soft docking on an asteroid, tether down and go out on EVAs for potential missions. And one of the problems they have is building robotics that can move around in low gravity. And I said, we'll take Carlson's creature things and we'll evolve a whole bunch of innovative robotics. Or we'll model part of the bloodstream and we'll do a huge amount of computing around binding with bad things in the bloodstream and really help people help in medicine.
Yeah. Can I add to that? Yes, there's philosophical questions, but there's also, things that are crass personal. what can you do? Well, you can grow structures from an architectural perspective. There's a great guy doing work on that with architects in Rotterdam. There's growing algorithms for pattern recognition. What kind of patterns? Well, for an oil company, it's growing pattern recognition for looking at identifying faults, saltums, and other sorts of underground features that are a result of sitting sound underground. These are very difficult things to do, and it's from a top-down intelligent design, if you will, approach to algorithm development. It doesn't seem to work. If you contrast it with things like neural nets or other techniques that have tried to use this, they're somewhat brittle. So I think from a practical perspective, it's finding oil, something like that. Building structures, say building domes or things like that. And there's a whole host of other very practical kinds of applications that are quite useful. But there is the larger issue that if you have demonstrated on a small scale, there's a logical progression of where you're going. Which is, I think, when you join this group prior to the discussion in the podcast, is what we're grappling with, is this idea of the philosophical issues of the work that we're doing. Almost to some extent, like perhaps, which is a bit hubristic, of what maybe people who were in the GreyThumb thought maybe struggled with, and ultimately set up the American Federation of Scientists.
Rachel.
I think the evolution of what's happening in artificial life is hugely relevant to biology, because I think there's a general assumption that we know how biology works. And only since about the year 2000 there have been huge developments in the field called astrobiology, where the very nature of life and its origins and exactly what constitutes it has shifted radically. So artificial life environments is hugely useful for testing biological principles of design. And like you were saying, architecture, you drawn from those as well. So we're only just developing new techniques in molecular biology to look at what these materials actually are and where they come from and how they might interact, which will challenge the dominant theories of evolution as we know it now. What we assume is correct to be natural selection, survival of the fittest, will actually turn out to be something, be modified in a certain way because of what we're understanding in molecular biology.
And Richard Dawkins, when I went to have tea with him in 2001, he said, there are two things I like about the idea. One is I can get at the creationists, because he was even then sort of engaging them. And the second thing is it will really force biology to come up with basic definitions of what do you mean by the components of a living system and the processes of a living system. This will be from a bottom up. It will be tremendously valuable. And consider, there's a way to make this testable. What if your Evo grid is running, and vacuoles are already reproducing, bubbles are making outer bubbles, and that's not very interesting, but the blokes have agreed to continue running it. They're running it. What if, like in Carl Sims' simulation, it's great to have a last name Sims when you make a simulation. I kid you not. What happened with him was when he put all these basic physics in, he found there was a turtle swimming thing came out, and then there's a fish swimming this way, and there was all the basic sort of morphology of motion came through. It's almost like they're mathematically winnowed down. What if in the Evo grid, if people are still running the Evo grid, they come up to a really sophisticated, these bubbles become really sophisticated. There's lots of machinery in them, lots and lots of machinery, and then you start seeing patterns, and you start seeing, that's a kind of Golgi apparatus. That's a kind of mitochondria, but it's different. But you see things converging together, not quite meeting. That's going to be profound because that's almost like testability. So then you say, this is actually really got something here. What we'll do is we'll go back and we'll have the blokes sign up for another EvoGrid session to run for another 10 years. But we now understand more of the physics of solution chemistry, and we're going to make it a little better. And then they're going to run it for another decade. And then the big EvoGrid objects that come out are like, that's really close to a paramecium in terms of the basic structure and the forms. Then you're really starting to get something as a tool.
If you look at the enzymatic pathways in the human body and how you model that, system dynamics is very, very similar to that. So there's the simulation aspect. So from the BCS, from the perspective of computer programmers, there's a lot to learn from the idea of approaching computer science from more of a biological perspective and actually harnessing the power of evolution and natural selection to effectively grow algorithms rather than focusing their attention on the top down. So for computer scientists who are interested in growing software, embracing this idea can be a very powerful mental model shift that once you've made it, frees you up, so to speak, from having to kind of create the ultimate algorithm. It's just one idea. I think there's a lot of insights that come out of biology.
I think there's one more.
Good.
First time I came across artificial intelligence and grid computing about a couple of years ago, almost 10, 15 years ago, when some medical professionals in the Leiden Biotransplant Center came across an algorithm to actually predict if a patient with A&E will survive, depending on the rhythm of breathing, blood pressure, and blood gases, and so on, and the algorithm around it. That's from there on, was done with really big supercomputer, and nowadays you can run those kind of things on little kind of little G5s from Apple. And if you look on what's now the done in the health industry with augmented virtual reality and pattern recognition, you can detect on X-rays, on CTs, for example, to assist clinicians to see the right kind of image or to build it into expert systems. So the algorithms will grow and will manage new functions. You see new cancers detect new viruses and model viruses, virus evolution.
And I think that there's another really interesting thing. I think in the 21st century we're going to look back sort of toward the end of the century and we're going to say the greatest new tool that emerged was our ability to harness the power of evolution. In wet biology, in Craig Venter's synthetic biology, where you're messing around with code at that level, and in software to do these kinds of things. And it'll permeate all of technology. I know that's you're predicating your business on. But we look back, and we'll look back at this period, and we'll think, how on earth did we design things without this? You know, of course, they've got models for buildings where optimal wind, they make holes in skyscrapers so the wind can go through and whatnot. And those are relatively simple, just simulations for optimization. But we'll wonder how on earth, and it could be that by the end of the 21st century, we'll say we couldn't have survived at all without harnessing this because we got into troubles around 2049, because I'm from California and the 49ers and everything. Around 2049, we hit a total disruptive event where the planet decided, you want monsoons? I'll give you monsoons in Mexico. You want droughts? I'll give you droughts in the UK. You screwed with me enough that I'm just going to turn over. And let's see how you deal with this. Because this has happened before with the planet. It's all let's have some fun. And so as a species, we'll be hit with this. We can't solve the problems fast enough. We're going to need to grow wheat in places we couldn't before. We're going to need to actually fabricate food in buildings to make it through this period. If we're going to sustain we'll drop a bunch of our population, and then we'll have to do all kinds of things faster and faster and faster as the biosphere gets more and more dynamic, trying to kind of throw us off. We're like, who's putting all this gas in here? Quick, melt all those ice caps to sort of suck up the gas. It's like everything's out of balance and heat up, and let's try this. Oh no, there's still the gases coming, and oh gee, what are we going to do now? And if the Earth was a thinking being, but the Earth is adjusting to us. In 2 billion years ago, just another last little story, I was in a gold mine in South Africa, and it wasn't that I was looking for my next grant support. I was just a tourist. But they took us down about 1,000 feet, and these are terrifying places. I'll tell you, I don't know how people could work there. They go down 5 kilometers in these mines now. It's 186 Fahrenheit. Anyway, I'm just wimpy. So they took us down on the tour, and they're coming along, and they're saying, now we're going to demonstrate the jackhammer. And the most terrifying sound, you're in a tunnel, and they're jackhammering away. This is South Africa. This is not a risk-averse society. And so there's pieces of tunnel coming off, and here you go, take this home. And it's all black. It's like got a sort of a shiny sheen to it, and suddenly it goes black on the surface. And they say, it's the gold reef. The gold reef was formed before there was oxygen in the atmosphere. We know this because when you held it up, it went black. And that all the gold doesn't have oxidization. All the gold, the stuff. And it was 2 billion years ago that the gold reef was set down by inland rivers pouring into this big delta. And all the gold was just like Panner's gold. And so what happened between that time when the gold was laid down and later was that life in the form of cyanobacteria and stromatolite, mushroom-like things around the continents was pumping pollution into the atmosphere called free oxygen, pumping and pumping and pumping. And it reached this break point where there was mass extinction everywhere. Oxygen diffused into the water, huge mass extinction of very small things in a big crisis. The adaptation was that some of these cells were like, we're surrounded by a toxin, oxygen, it'll bind to anything, it just completely gums up the works. But I'm a lucky little cell because this morning I ate another little cell that's now around in my tummy, and it was upsetting my tummy except that it's taken up all that oxygen. So I'm happy. I didn't get killed. And that was the beginning of cells being able to create energy at a huge, the ATP cycle, whatnot. You're the expert here. But so that rapid adaptation, it was an accident, caused life not only to survive a very big disjunctive change, but to lead to big things that needed energy and big bodies and stuff. Wouldn't have been possible without a huge pollution of the atmosphere. We as a species are putting carbon dioxide back in, and some of the species on Earth are goodies like the old days. There used to be a lot more of this stuff around. We're happy, but it's not going to be very happy for a lot of species. So again, there will be this disjointed evolution, but we are going to use our intelligence and our tools to probably get through it. And we'll do it at the last minute. This is the way we are. But maybe Justin's company will build some of the tools that will lead to that solution. But I think that the power of evolution, whether or not you believe in it or that God created the earth, it's a non-issue. We're going to have to use that tool that we see working on a daily basis, I think, to survive and thrive as a species and to go outside of our world.
Anything you want to add anything on?
Drop me an email if you want to continue the conversation.
Any more questions?
I just wonder if it's going too far to wonder whether, with the evolution of a life, is it then conceivable that within that there could be the evolution of intelligent a life?
I think it's a big jump.
Yeah.
I don't believe in the singularity and things like that. Unless the entire internet, creating this group mind of Twitter, is creating a singularity out of all of our minds. But I think it took so long for intelligence to arise. I think that if we end up having an evil grid where all kinds of stuff is going on, it'll be like just having a biological laboratory alongside. Now the interesting, one more real magical moment is, say for instance, the evil grid has gone on fairly long. You've run the evil grid several times to generate your targets the following. To make the mathematical algorithms make a thing that you know you can make in wet chemistry. Right? So you run and run and run and run and run it, and you say, all these things may be kind of pseudo life forms, but this one has the right math and the right structure. We can replicate that thing in a bilipid layer. We can use chemistry to do this, and it may be not completely CGA. It may be different, slightly different chemistry, different components, lithium or who knows. And so we actually go into the lab and we fab one of the things. We fab it, and then we put it into solution. And that'll be quite a moment. It's like, walk, baby, walk. Please survive. Everybody's just roaring for it because it's been in the chrysalis. And if the thing actually it'll probably poop out and explode and fall apart right away. But you keep trying, and maybe you'll get one that it's a replica of the thing that was in the evil grid, and it actually can survive. And the biology of that cell is different. It's just different mechanisms, maybe slightly different, maybe greatly different. But we're watching the thing swimming along and making a copy, and it's not Terran biology, but is it?
To add to this, what I want to say, Craig Venter is working on artificial life. And I showed the slide about the innovators and the early adopters in this tipping point. Great Venture was a classic example. We had this thing called the National Institutes of Health and the Genome Project, which is this massively funded $1 billion thing that takes 10 years on. And Craig stood up and said, yeah, this is stupid. I can do it a lot quicker in the private industry. And all the academics just jumped on it and said, no, you can't do that. Similarly, okay, I believe fundamentally that we've reached this tipping point. And sometimes even the pioneers and the innovators who came up with this stuff, they'll probably hate the people that come along and commercialize it, okay, who actually say, you know what, we can find oil with this. You know what, we can reduce risk with this. So that's where I think we're at with this. Same thing that happened in 1994 with the internet, the invention of the World Wide Web. I was on these advanced HTML listservs where people talking about syntax, my God, that's not what we're supposed to be doing. And then David Filo, Google, jets, billionaires. So I think that I think we're at that point now where this stuff is commercially viable. It's not. I mean, it's yes. There's fundamental questions, but you can actually use it to actually accomplish things right now, next Monday, in a board meeting. Actually, do real things. I just might want to put the
How are we doing on ours?
Okay, one more question. Somebody else got a question?
Larry, you got it.
Well, I'm just going to support your claim that this can be used today for real things. Dirk Helbing, I think Tübingen, is doing studies of vehicular traffic flow with these multi-agent systems, and being able to actually advise governments in order to how to improve their traffic flow. Eric Bonobo, Boston, has been doing studies of crowd control, and with the multi-agent system produced the seemingly non-intuitive, until you understand what's going on, result that the way to save the most number of people rushing out of a burning building is to put barriers in front of the door. Sounds completely illogical until you realize what it does is it forces the traffic, the people running towards the door, to slow down, and it organizes the traffic in such a way that more people get out of the room alive. So these tools are being applied today routinely and being very useful. If I can throw in one more tidbit, I would say don't underestimate the power of natural selection, though. I'd like to tell us another Carl Sims story, but I don't want to take up too much time here. Carl Sims, was doing these critters, also had, he has a physics engine in there. It has to in order to do the swimming and the walking and so on. And he had another bug in the program. He told you on the TV clip about the things that would grow straight up. Well, he had another bug that he has a collision detection algorithm to figure out when one polygon is touching another. And the way the algorithm works, they first interpenetrate, and that's normal, expected. And what your algorithm does is find this out and then push them a little bit apart. But there was a bug that if they interpenetrated by less than the precision with which he was measuring his numbers, he would get a 0 in the denominator, and these things would jump all the way to they try to go to infinity, and then some boundary condition would kick in, and they would stop at the edge of the world. And these agents, this really obscure bug in the system, evolution happily found that the agents started rubbing their own body parts together, slowly, until they just crossed this threshold, and then bing, they teleport to the edge of the world. And it moved their center of mass a very long ways indeed, and so they took over the world. Everyone who has ever done one of these A-Life systems, myself included, can tell you stories how evolution found solutions that you never imagined were in the system at all. And so I actually think that, in answer to your question, that it will get to intelligence. I think starting with artificial chemistry is problematic for getting to intelligent behavior anytime soon, just because of the number of levels of organization that have involved. But as Chris Langton, the father of the field, said, everyone who does this, you have to write an IOU at some level. And so there are those of us who have decided to write the IOU at a little higher level. That's why I start with nervous systems evolving. And I think that I'm not trying to get to human level intelligence just yet. A computational aplesia is all right. A C-slug is all right. But there's lots of, if you look in the animal cognition literature, there's all this wonderful stuff about sort of amazing abilities of 250,000 neuron fruit flies. 1 million neuron bees can learn the difference between, can learn the abstract concept of same versus different. It goes on and on and on. There are great examples throughout invertebrates and vertebrates of a kind of lower level intelligence that I think we can begin to evolve our way up this spectrum of intelligence. And I don't think it's an insurmountable goal.
And of course, we all know how fallible human intelligence is, so that as it's approaching human intelligence, we should nudge it and be more sensible next time. Then, of course, they'll become conscious and sentient and look at, you people are crazy. Look at how you operate. We're so much better. Then we'll have something that's in negotiation at that point. There's be so much better than we are. They won't be able to play poker or gamble our mortgages and do bubbles, and so that we'll become like World of Warcraft to them. It's like these things are so crazy, you can play these games with them, and they do all these crazy things you can't predict, and nobody knows why, but we know why, because they were evolved by natural selection and chemistry, and there was nobody there to nudge them into better behaviors at a certain point. So we'll be in the zoo.
Like new temptation.
Right.
Sorry, just in case people think that there's some kind of leap of faith being made between transporting virtual models into the real world, we've now got computer programs that can print off tissue cell cultures made over bioscaffolding, and now we can print artificial livers, artificial hearts, and these printed models can actually interconnect and continue to grow. So they're being exported from the virtual reality into a biological world.
So I want to issue an open call. If you're interested in this subject, I now know Rachel's passionate about this and has some of the answers, please contact me at bruce@damer.com, or simply go to damer.com and click on the little envelope or something, because I'd love to. We're building a community effort around. I'm going to go back to Richard Dawkins, try to get on his T appointment list, say we're going to build this thing, because he was interested in before. Will you put your name to it? It won't take much time. We'll come to you in 50 years when we have something to show, and try to get him on board. But we're getting a lot of people on board who are fasted from the original Biota conference series and recruiting people to do the thinking. They'll be thinking about algorithms. They'll be thinking about philosophy, various things. And out of that community, what I'm hoping to do is derive this PhD publication book, this big book, and perhaps even get the project started, although that's probably pretty ambitious for a 3-year.
Just join the conversation, Biota.
Biota.org.
Biota.org. Drop me an email. This is Justin. Justin at City.com.
If you want to make money out of it, talk to him. If you don't want to make money but spend lots of time thinking about it, talk to me.